Good evening and a warm welcome from Physics for Students and a very warm welcome to today's session. Let me introduce myself. My name is Shaunak. Those who don't know me, I run this channel and I'm a teacher of physics and mathematics, specializing on the relativistic part of relativity. I teach differential geometry, the basic mathematics, as well as I teach some part of quantum field theory and the basics of quantum mechanics. By profession, I am a teacher. I work with a university for professional reason. I cannot tell the name, both in India and international. And I am a PhD advisor helping students to complete their PhD in the subjects. And I'm also evaluating their thesis paper, helping them to complete PhD in an effective manner. So that is a little bit about myself and a warm welcome to today's session. And in this session, I would try to cover the general theory of relativity, Einstein's general theory of relativity. And this would be basically covering almost all the aspects of relativity. So with that, let me go ahead and start with today's presentation. First of all, let me explain to you what is general theory of relativity. Well, as we know that it has been discovered by Albert Einstein around 1915. So it took almost 10 years for Einstein to complete after he published his special theory of relativity. Those who are watching, can you just tell me whether my audio is clear or not? Because sometimes it happens that the audio part is clear or not. If you can just put it up in the comment box, yes or no, that would be great. So what happened is that we generally think relativity as a wrong, something special relativity or Newtonian mechanics is wrong, but that is not the fact. The fact is that it refined special theory of relativity. So as you can see on the screen, the left-hand side, which were straight lines and which obeyed their Newtonian mechanics and the Pythagoras' rule to actually calculate the distances, are now called geodesics, which was considered to be space and time to be different. Just a second. Okay, great. Rudra Pratap Singh, Vincent Pinto, wonderful. Okay, so which was considered to be a space and time as two different or three different axes. With geodesics, will you cover this in the video? Yeah, I will definitely cover geodesics, definitely, Rudra Pratap Singh. So just hold on, because this is going to be a little bit more detailed approach towards relativity. So just hold on for a second and I will just cover up all the details. So that part is there. And what Newton conceived that as a force, F equals to ma. We will soon see that how F equal to ma got changed. That concept of force is considered to be as a space-time curvature. So there is a heavy mass on a trampoline. The mass is creating a curvature, a dent, right? And all the planets and everything is going around, not because of force, but because of the space-time curvature. I will cover up what do I mean by that. So straight line got generalized to geodesics. Space and time, which was different, came to be a space-time continuum. And force F equals to ma become what Rudra Pratap Singh rightly told as a geodesic. So it is not just a theory of gravity, but it is a new way of watching things in a different manner. So from here, as you can see that what was thought to be as a fixed time as an axis and everything, I will try to do that. Thank you, Mr. Raghav Manchanda. Raghav is there, right? With Professor G. Srinivasan, I will try to do that. We have a very important podcast I have not announced coming up on the 6th of, this is what, September. And this is regarding general relativity only. A very renowned professor, Dr. Bhashyati, is coming. I will announce that in the channel. So space and time was thought to be different. Time flowed in uniformly, and general relativity actually united space and time together in this kind of a space-time continuum. And also the notion of inertia changed, because inertia during, love you sir, I'm fallen in love with physics like you. I hope I will meet you in future. Who is this? Bodhanta. Okay. Okay, thank you, Bodhanta. It is good that you have fallen in love with physics, and it is wonderful. Surely I keep in hope that we will meet you. Francisco George from Brazil, Rio de Janeiro. Welcome, Francisco. Warm welcome to today's session. And it's a warm welcome from India. My name is Shaunak. Okay. So these two masses were experimentally equal, but Newton thought it to be two different things. So gravitational mass to Newton appeared to be different, inertial mass appeared to be different. And we will see how this actually united by what is called the happiest moment in Einstein's life. So these two things, inertia and gravitational mass, were thought to be different. Now here you see in special theory of relativity, mass and energy were equivalent. I mean to say mass turns to energy, energy turns to mass. This is through Einstein's E equals to mc squared. And remember that this mass is no longer just a weight like a body or a paper weight or something like that, which is there. So this mass is actually consisting of everything. It consisted of pressure, temperature, radiation, everything together comprised of the mass. And this mass is causing the curvature. So you can see right on the screen that if there is a ball on a trampoline, this ball is responsible for the curvature. So what is responsible for the curvature? It is the mass. And the mass is not just the typical Newtonian mass, but we will see that it covered inertial mass, it covered radiation, stress, flux, every single thing. So the planets orbit not because they are pulled by something, but it is because of this dent. You can see, I cannot show the animation right now. You can find it in internet that it goes around and around and around. And geodesic in curved space-time is thought to be a straightest possible path. That means right on the screen, you can see this red dot. The red dot moves in a straight line. I will explore these things. It moves in a straight line, but because the sphere has got a positive curvature, it seems that it is going in a curved space, but actually it is not. It is moving in a straight line, but the path or the platform in which it is moving is because it is curved, so it appears to be a curved space-time. I will cover up that part. Now, this is actually, we can say in short, what is called a general theory of relativity. Now, you might have a question in mind that why it is called general. That means, is it something that there is something special? So these are two contrasts, right? One is special, one is general. So why it is called general? Let us find it out in a very simple words. Now on the left hand side, you can see this boy is tossing up a coin. I created this in Sora, and Sora nowadays are creating great images of ChatGPT. So the boy is throwing up a ball right on, and the train is moving at a constant velocity. That means what? It is not accelerating. It is at a constant velocity. And hence the ball goes up in a parabola and it goes down. It goes up and goes down. So this was actually Einstein's idea in terms of special relativity. Now suppose the train is accelerating. That means it is moving, accelerating, going at a high speed, or it is changing. So in that case, as you can see on the right hand side, the ball actually is not going up and down, but the ball is moving a little bit forward. So general theory of relativity, the reason it is called general is that it is not special that it will only apply to constant velocity or acceleration. No, it is also applying to areas where it is not in constant velocity, and we will see what are those areas actually. So you can see that on the right hand side, the boy extends the hand. That means the ball is moving at an accelerated frame of reference. So Einstein thought that why don't I change from special reference that is only accelerated frame to non-accelerated frame of reference. Now here you can see this diagram actually shows that general means that it will apply to all frames of reference. Number one, it will apply to accelerating frame. Number two, it will apply to things that spin, or as you can see, if there is a kind of a kind of a axis like this, if the axis rotates like this, if it turns around like this, so whatever is happening to the axis in case of a coordinate transformation, this will also take place there. That means the laws of physics will be the same. Whatever is happening, it won't change. And in gravitational frames, when you are standing on the Earth's surface, that means, as you can see right at the bottom of the screen, that if you are floating in deep space, freely in deep space, there also it will be applicable. If you're falling into a black hole, there also it is applicable. And if you're riding a roller coaster, there also it is applicable. So whatever the areas that you're moving in, all the laws of physics will be the same. There won't be any changes. And that is why it is called general. General means it is not special. Not special means it is not only applicable to accelerated inertial frame, but also in non-inertial frame of reference. Now, I will come to this part very briefly, that how actually Einstein's general relativity was discovered. Now, here you can see that this is actually the original paper, although in many of my videos on my channel, I've also got a new channel which I'm not telling you because I'm not active in that channel. It has now been renamed from General Relativity Explained to call Physics Musing. Now, this is actually the original paper which Einstein published in 1915. So it is written in German. The translation is The Field Equations of Gravity. And this actually marked the birth of general theory of relativity. Although there is a debate that David Hilbert published to before that, we are not going into in the debate. But this is what the Einstein general relativity was discovered. Okay, here comes a kind of a brief idea that how general relativity was discovered. So here you can see that during 1907 to 1915, Einstein thought, which is called the happiest moment in his life. Okay, and you can see right in the screen. Okay, let me just stop the screen sharing and let me explain this to you. So, for example, if I am standing on Earth, this is very important for understanding. What I told you at the beginning is that what Newton thought that gravitational mass and inertial mass is different. This is not. So, if I'm standing on Earth, say for example, these are my 2 feet which is standing. So, I feel a kind of a pressure due to the gravity or due to this from the bottom of the Earth. So my 2 legs are feeling the pressure. Okay. Now, if suppose I'm on an elevator and that elevator is pushing me up. So this is the elevator and this is pushing me up. I will feel the same kind of a thrust on my feet. And I experience this every time I move to my college and university, because my university is located quite above, and every day I have to stand on the elevator. And I think that this is actually what Einstein thought 100 and 150 years back. So here I am standing, I am feeling the same pressure. And here I am where the elevator is pushing up, I am feeling the same pressure. Now, say for example, God forbid the floor collapses and I'm falling in deep space. So what I am feeling is I am feeling weightless. Okay, I'm floating in deep space and I'm falling, I'm feeling free. Okay, I'm feeling weightless. Now, same thing happens, God forbid, that when I'm standing on the lift and the wire of the lifts are no more there and the lift is falling. So if the lift is falling and I'm falling, lift is falling, I'm falling, if I drop a ball, the ball will float in the air. The ball is going to float in there. What does it mean? That means standing on Earth and feeling the pressure and moving up the elevator does not make any difference. The same pressure I will feel while I'm sitting here and the same pressure I will feel when the elevator is pushing me up. Similarly, when I'm falling in deep space, whatever the body will feel will be the same when the elevator is also freely falling. That is what is called the equivalence principle. And as you can see, I have illustrated here on this part of the video that the gravitational field only has a relative experience. That means there is nothing which is a universal gravitational field. And right hand side, as you can see, the girl is sitting on a box, feels the same pressure, and the ball and the girl falling also feels the same pressure. So because an observer is freely falling from the roof, at least in his immediate surrounding, there exists no gravitational field. This is very important. There is actually no gravitational field. So standing and moving up and falling and the elevator is falling actually has no difference. Equivalence. What do we mean by equivalent? These are equal. So standing and falling, though both of them are equal. So that is what Einstein called the happiest moment in my life. So are you all following me? I know that you must be very intensively watching this. So just put up a comment from time to time. I feel that a little bit of comment actually helps me to understand. So, and there's a very interesting history. I'm not going on that because we have to cover a lot of things. Now, it was Marcel Grossmann, Einstein's friend. He's a Swiss mathematician who has got a book on differential geometry, if you have read it. Now, he actually knew what is called tensors. He actually knew what are called, Riemannian geometry. And Einstein was actually struggling to find out what is. Yes, excellent. Who is this? Vincent Pinto. Okay, thank you, Vincent. So actually what was happening is that does the frame of reference affects the gravity affecting the accelerator? Rudra Pratap, no, the frame of reference do not affect the gravity. What do you think, Rudra Pratap, as a gravity? Is not that gravity as a force. Okay, so the frame of reference does not reflect gravity. That is what is the equivalence principle. Irrespective of whatever the frame of reference, it will be the same. Okay, so Marcel Grossmann was a master of differential geometry, Riemannian manifold and Riemannian geometry, etc. And as you can see, this is on the screen. This is actually what was called the seed of general relativity. That means Einstein and Marcel Grossmann together, what is called the Entwurf document. Okay, Entwurf. Entwurf in German means a draft. So that was the first draft which Marcel Grossmann and Einstein, because Marcel Grossmann actually, thank you, Rudra Pratap. So Marcel Grossmann actually taught Einstein about Riemannian geometry, tensors, Ricci tensor, curvature tensor, etc. Because history says, and Einstein even admitted, he had no idea about differential geometry. Albert Einstein had no idea about tensor calculus. So this Entwurf document was very important. I don't know if you know how to read German. If you can read it, you will be amazed that if you go to my, just a second, hold on. I will just give you one of my Facebook link. Here you can go, and I'm actually, I'm just sending it to you. Those who are interested can follow me. You can follow me in this page. And here actually the German words, that original documents, I'm putting up a translation where you will actually find how Einstein was creating general relativity, the original handwriting of Albert Einstein, Marcel Grossmann collaboration. You can follow me on my page, Physics Compass. It is very interesting. I'm putting up a lot of important histories, facts, etc. For facebook.com Physics Compass. You can follow me here. And also what you can follow me on my thread. Nowadays, I can find that this thread is becoming a little bit, popular. I'm putting it up here. Also, I'm putting up some important and interesting facts about physics. So it is not only, things which are related to. This is my thread link. Okay, you can follow me. Indrarup Sen. Sir, I want to pursue general relativity and cosmology in my PhD, and I'm an undergraduate at present. I'm doing MSc. I'm doing BSc in mathematics present. Then which degree I do next to that? Okay, Indrarup, because we are discussing this thing, what I would request you, get in touch with me. I will give you my WhatsApp number, 98302196777. After this lecture, maybe tomorrow, you can just get in touch with me. I will tell you, I will talk to you, and I will find out what are the things that you like, and then I will give you idea about that. You're doing BSc in mathematics. After that, you want to pursue PhD in general relativity. Good. Get in touch with me. I will let you know, and I hope I can connect with some of the good professors of general relativity also. Okay. So this is how it was being found. Now we come to the core idea of force. Core idea of force in the sense that because we know that general relativity totally what I would say, totally changed our notion of force. So we will now see how the equation, very thanks to you, sir. Okay, thank you. Thank you very much in the group. Get in touch with me. So here, as you can see, that the core idea of force has changed. So we will see how simply the equations of Newton was now being modified in the idea of general relativity. Okay. So first you see that this concept force as itself, now this is very important and very deep. Now, as you can understand, the man is pushing the box. So in Newtonian mechanics, force is basically the fundamental cause of motion. Now here you need to be a little bit attentive. Okay, force is the cause of motion. This is the basic idea of Newtonian mechanics. And similarly, gravity is actually a kind of a force. So we see that famous Newton's apple, which is falling down. So that is how that gravity actually pulls the object. So this is all about force as far as Newtonian mechanics is concerned. Now, Newton's picture had a problem that instead of gravity, Einstein represented as a property of space-time. Now, the thing is that if the Earth is going around the sun, then what is that force which is keeping the Earth or other planets moving? There was no answer during that time. And believe me, I will tell you, there is a famous book, if you have read, it is a very heavy book, but there's I think Rupa Publications have got a, what you call the abridged version. It is called Never at Rest. Okay, just me find out the author's name. Never at Rest. Never at Rest. This is written by Richard S. Westphal. Okay, you can find it at Amazon. A little bit costly book, but try to find out the e-version. Never at Rest is actually the life of Isaac Newton, where if you read, then you will see that Isaac Newton even doubted, and he thought that he was not going in the right direction. That means what he's thinking to be action at a distance or a fictitious force, he was actually not happy. Isaac Newton was actually not happy. This was in the Richard Westphal's book, Never at Rest. I think a 1,000-page book, but it is worth moving. But space-time tells matter how to move, and matter tells space-time how to curve. Do you know who actually quoted this term? If you know, please put it up in the comment box. This is by famous physicist. Space-time tells matter how to move, and matter tells space-time how to curve. So as the ball drops on the trampoline, it creates a kind of a curvature. So here you can see. Now hold on. So the mass causes a curvature. Okay. So instead of force acting at a distance, Einstein thought that it is basically the mass and energy which is causing the curvature. Now this F equals to ma. No, not Feynman. Yes, Vincent Pinto, right. John Wheeler. Yeah, absolutely, Vinto. Bingo. You have got it right. It was not Feynman, it was John Wheeler. So John Wheeler actually quoted this term. So now here you can see that the F equals to ma, that famous equation, actually got reduced to what is called a geodesic equation. I will come to this geodesic equation in a few minutes. Rudra Pratap was asking that. So what was the basic idea? Newton's answer was, in empty space, things move in a straight line. Okay, it is moving in a straight line until there is a force which is pushing things apart. Einstein's answer was that in space-time, okay, he has, okay, thank you, not a problem. You're welcome, Walter. So Einstein thought that in space-time, which causes the curvature, straight lines are repressed by geodesics. Geodesics actually means that if there is a particle which is falling in free space, I don't know how to demonstrate, it will always follow this path. It will always follow. That is why you will see that in geodesic equation, it is equal to 0. If you follow my other lectures in general relativity, mathematically I have to say, equal to 0 means there is no external force. So if this is falling, it won't push things away. That is why the geodesic equation is equal to 0. Okay. So Einstein's answer was this. So objects move naturally. Okay. Just like Newton said, nothing extra. But mass causes the curvature, and it looks as if that the light or the particle is bending. So it is basically what is called the geodesic. I will come to this part. Don't worry. I will explain to you today. Now, here you see F equals to ma. Okay, just hold on. Just watch this. None of the professors except you I have met who are so much student friendly, despite having too much knowledge in this field. You are exceptional. Thank you, Indrarup Sen. I don't know from which part of India or world you are, but thank you very much. I'm really obliged by this comment. Thank you. I always try to be friendly with the students. Okay, coming back to business. F equals to ma is Newton's second law. Okay. But what is acceleration? Try to understand. Acceleration is the second derivative of time. Simple. Class 12 mathematics. Okay. So if I now substitute a equals to second derivative of space, d square x, and dt squared, then if I put this a into f equals to ma, what I get is f equals to m d square x by dt square. Simple. I have substituted acceleration in f equals to ma. Done. Now here you see that in Newton's view, force is the cause and the curvature of trajectory, that is acceleration. Einstein's removed the idea of force and put it as a curved space-time. Now here you can see, I'm not going to explain it because there are Christoffel symbols, etc., which will take some time. But here do you see something very remarkable? You see the equation F equals to ma, a part d square x and dt square. Now in the geodesic equation, do you see the same thing? D square x mu by d tau squared. Again, let me repeat. A, acceleration is d square x by dt square. Is it all clear? I mean to say, are you following me? Please let me know. And in the geodesic equation, it is d square x mu by d tau squared. Do you find any difference? No. That is also the second derivative of position and the second derivative of time. Here also it is the same thing. That means what Einstein derived is basically the same acceleration concept which Newton has derived. Only this x mu, because Newton thought, okay, most of the professors just ignore. No, I never ignored the questions. Wherever I teach, I always take the questions first. So the basic thing is that in acceleration, we have a d square x. In geodesic equation, we have a d square x mu. Same thing. In acceleration, in the denominator, we have a dt squared. In geodesic, we have a d tau squared. Only Newton considered space and time to be different. Okay. Einstein considers space and time to be one. And in order to do that, he actually substituted mu as 0, 1, 2, 3. That is 0 for time and 1, 2, 3 is for space. So here you can see d squared x by dt square is the second derivative, and d square x mu by d tau square is also the second derivative. Only thing that he put is the Christoffel symbol. Okay, and this actually encodes the curvature of space-time. This thing I will come later. You can even watch my videos on geodesic equation. I won't cover that, but because so what we understand from here, the core idea of force, nothing actually changed. Acceleration remained acceleration, second derivative remained second derivative. Only there is an addition of the space-time coordinate, the mu part, and because there is a time dilation and length contraction in special relativity, Einstein introduced the concept of proper time. This proper time is the same as the time t, but taken as tau squared. So nothing actually changes. General relativity is, yes, absolutely, Rudra Pratap. 1, 2, 3 refers to the dimension. 0 for, we will come to that when we are dealing with Schwarzschild metric, we will come to that. Okay, so 1, 2, 3 refers to the spatial direction and 0 for the time dimension. So actually general relativity is very simple. You see that now it is revealing slowly. I hope you will get more interest. Okay. Now I will briefly come to, I will come to this part later, but overall I will just explain you what is Einstein field equation. It is not equation, it is called equations. There are many equations which are hidden over there. I'm thinking to purchase a kind of a speaker, because right now I don't need to hear. So this is creating a lot of trouble in my ears. It is so anybody can suggest a good microphone for YouTube making. You can just let me know, because I'm not a tech guy, so I don't know which one to purchase. Okay, so what is Einstein field equation? Now here you see that Einstein field equation actually is basically the core mathematics of general relativity. Okay. All these are different forms. You don't have to understand all of this. Standard form, original form, geometric form, trace reverse form, okay, compact form, etc. But try to concentrate on the right-hand side of the equation of your screen. Okay, this is what we are going to learn. So entire left-hand side measures the curvature. Don't worry, I will tell you each and every component of that. Okay, it measures the curvature. That means, say for example, if I take this kind of a cloth. Okay, and if I bend it, say for example, so how much it is bending, this will be caused by the curvature. This is going to measure, and on the right hand side is the matter. Okay, sir, I have studied entire tensor calculus in detail. I do understand basics, but I'm stuck at the second fundamental form. I cannot just get the intuition of it. Please help. Yeah, all these things I will come to after this lecture, because if I keep on talking, the other viewers won't be enjoying that. So let me know on the second and the first fundamental form. I will come to that part. Let me know after you connect with me. Okay. So again, it is telling space-time matter tells matter how to move, and matter tells space-time how to curve. So this is the left-hand side and this is the right-hand side. Okay. Now, how actually the birth of Einstein field equations took place? So again, I don't want to repeat. This is the same equivalence principle which came up, and this is basically a repetition. So I am ignoring this, and you know how it tells. Okay. I will come now to what actually it tells. That means, what is Einstein field equation actually telling? So first of all, what it is telling is that gravity is not a force. You already know that. Okay. And Newtonian physics, the entire gravity, the equation of Newton's gravity now is being replaced by Einstein field equation. Now, here I would like to pause. How will I explain? The concept of Newton's law, F equals to g m1 m2 upon r squared, this is not a field equation. Are you getting my point? This is actually what is called the force equation. Now, in between, so if I take Newton's F equals to g, that equation, and if I take Einstein field equation, it won't match, because this one, from this one you cannot go back to that, because this one is a field equation, Einstein's, and this one is a force equation. How will we made? I have made a video, you can go into that. That is basically what is called Poisson's equation, P-O-I-S-S-O-N. Poisson's equation, or Poisson's law of gravity, equation of gravity, is actually a field form of Newton's law. So you cannot compare a pin to an elephant, right? You cannot compare oranges to apples. You have to compare oranges to oranges. So in order to compare a field equation to field equation, you need another field equation. So Newton's law of gravity was later modified by Poisson, which is called Poisson's field equation, which can be traced back to Einstein's equation. So don't think that from Newton's equation we cannot get back to Einstein's equation. In between we need a field equation. Okay, so here you can see that this is the famous light actually bends, and this actually was the first. We will come to the tests later. So Arthur Eddington during 29th of May 1915 actually made two expeditions, one in Principe and another in South Africa. And it was during the solar eclipse, and it was found that light actually deflects. Why? Because during the solar eclipse, the sun comes nearer, and as it comes nearer, its mass is heavy. So because of the mass, there is a dent in the space-time curvature, and from there, the light actually bends. So this is the newspaper cutting of the famous Einstein experiment. Okay. Now we come to the Einstein's field equation. Very importantly, here we are going to learn all the components. Okay. So first of all, you already know, I am taking this form, but don't, my viewers and students, don't get confused. There are various forms of equation. I have taken this one because I want to explore each and every component in detail. So I'm not taking the shortcut or the vacuum form. That would create confusion among students. And I've seen that students get confused. So always take a bigger equation. I was making a short video on how to select the mathematics book. So there also, take a heavy book. Don't take 200, 300 pages, because heavy books are better. They explain to you. Okay. So here you can see, you know already the constants. One is the lambda, which is the cosmological constant. We will come to that part. 8 pi is a constant. G is the gravitational constant. But remember, this gravitational constant will be changed in modified theories of gravity. On the 6th of September, we have a special podcast on that. So G means is a constant. Constant gives us an idea that things won't go beyond this limit. So it is a constant, right? 2.33. That means it won't go beyond that. So this actually shows that how Einstein's field equation are consistent. That means there is no extra thing that we need to move. Are you getting my point? So a larger G means gravity is stronger. C to the power 4, speed of light in 4 dimension, and 8 pi G C4. This is actually coming from a Poisson equation derivation. I'm not going to that. So these are the constants which you already know. Okay. Now first component. Now note it very carefully. If you have a question, do let me know, because this is intense. R mu nu. Now you see there are two R's. One has got a mu nu. Indrarup might be already smiling because he has gone through tensor calculus, and another without any mu nu. What does that mean? Now the first R mu nu is a tensor component. So it has got two indices. Mu and nu are basically space and time. I will show you that. And another R has got no mu nu. What does it mean? I will come to that part also. So R mu nu tells how volumes changes in curved space. So you have got a ball, as you can see. If you move the ball slowly, you see that the volume shrinks. And the volume shrinks because of a positive curvature. So on the right hand side, I have seen that if you are moving parallelly, nothing happens. So Ricci tensor is 0. If it is converging, Ricci tensor is greater than 0. And if it is diverging, Ricci tensor is less than 0. Just hold on for a second. I will have a glass of water. So how are you enjoying? Just let me know. I've been talking. I need your reactions also. Okay. Nobody is reacting. Maybe they are taking notes or whatever. So this is the Ricci curvature tensor that actually tells how volumes, and by volume I mean to say differential volume, not the classical volume, how it changes. Okay, so this is how things actually move and they actually converge at a point. So this is called Ricci curvature tensor. Okay, now you see the next tensor. You are enjoying Somnath Safi. Okay, thank you Somnath for responding. Thank you very much. Okay, the next R is called the scalar curvature. Very good. It is high speed, but we understand you have a lot to complete. Okay, so shall I go a little bit slow? Okay, no, I am not. You can watch this podcast later because it is live, right? You can watch it later. So the second R is basically called the Ricci scalar. Now, what does this scalar mean? Now, here you can see, if I go back to the screen, so you can just wanted to confirm one thing. Are you all being able to see my presentation? I mean to say the equations and the graphs, all of you can see when I shift my screens, it is visible, right? Okay. So the R here is got a mu nu, as I told, it is a what is called a tensor component. This has not got any mu nu. That means it is a scalar. So what do we mean by scalar? Okay, Vincent is telling. Vincent, thank you for being so active. So a scalar means what? Scalar means it is not showing any direction, just ordinary definition of a scalar. That means what it tells that if you have got a room, okay, and if you have it, so if you have got a room and if you're measuring the temperature of that room, R mu nu, the earlier one, tells how hot or cold it is in different corners of the room. Here, 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 here. That is why we got the mu nu. That is the indices, left, right, space-time direction. But if I take R, simple R, this is a scalar curvature. That means it's an average temperature of the room. Okay. You are doing fine. I have not been engaged in higher level math and physics lately. Like I was when I first started watching you. I saw you were on, so I decided to watch. Thank you very much, Walter. From which part of the world you are coming, please do let me know. So this is the average temperature. So average means what? We don't need the direction. So the Ricci scalar gives you the average temperature of the room. Okay. So it is a directionless summary and space without its magnitude. Absolutely. This is the central part. Abhijit Kumar, differential equation. Space without magnitude. So now we got one which has got space with magnitude, talking with Abhijit's language, which has got a direction. This has got no direction. That means it is summing up all the curvature and it is giving you an average. So that is why I have seen this sectional curvature. I'm not going in that. So this is the next R. I'm in the US, about 70 miles west of New York City. Thank you very much, Walter. Thank you for logging in from US. So the Ricci scalar tells you how the volume of a tiny geodesic ball deviates from the Euclidean space. So here you can see in a general Euclidean space, it would have been different, parallel, etc. But here it is deviating. So it is slowly becoming smaller and smaller. And this is the average one. Okay. Now, this is the heart. You know, we call the heart is in our body. If it stops pumping, everything goes for a toss. So this G mu nu is the metric tensor. Go to my channel, this channel, Physics for Students. You will find a very detailed, that was very long. I think 3 years back, I made a detailed video on metric tensor. So because I have mentioned this for beginners, so I won't go into the covariant, contravariant derivatives, which might be very interesting for Indra and others. But metric tensor is what is a ruler. So you have a ruler and you measure what? Angles, distances, isn't it? How much it is changing from this direction. Metric tensor is the same, but this is for the curved space-time. So metric tensor actually tells that how distances and angles changes in curved space-time. So here you can see in a flat space-time, the line is from this point to this point. If I plot that same thing, on a sphere, it will become different. Now you might have a question for me that Shaunak, tell me that for spherical coordinates, for hyperbolic coordinates, things will change. Yes, and that is what is the job of the metric tensor. From flat space, if you're moving to a spherical coordinate, if you're moving to a hyperbolic coordinate, you're moving to elliptical coordinates, metric tensor will change, and that is the beauty. It shows invariant nature. That means the basic physics will always be the same. So this G, again, it is a metric tensor. Okay, that is why it has got a mu nu. So the distance formula, x square equal to b square plus p square, will now become like this. ds square is equal to g mu nu, all those things, which I am not covering, which is a little bit technical. This is called the metric tensor. So what we have learned till now, we have learned what is called the r mu nu, which tells how volumes change. This is a tensor component. Then we came to the scalar component, which is the average curvature. And then we came to the metric tensor, which is like a ruler. It tells you how distance and angles are computed, but in a curved space-time. Okay, here you can see, I have explained this. This was I was talking about. In flat space-time, you can see this ds square equal to dx square plus dy square. Okay, so if I plot it in a linear algebra form, you can see this is 1, 0, 0, 1. Okay, so here the metric tensor is just an identity matrix. So remember that in flat space, which is flat, the metric tensor is just an identity matrix. You can diagonalize and you can see 1, 1 and 0, 0. Okay, but in case of a curved space-time, this won't be there. So there is no cross term like dx, dy, coefficients are 1, distance, scalar, uniform, there is no problem. But the moment you take this flat space-time Cartesian coordinate to a spherical coordinate, here you can see I've drawn that sphere. You can see these things are becoming different. So you have got a sine squared theta, then you have got a d phi square, and then at the bottom of the screen, you can see that metric tensor is totally different. R squared sine square theta. Then you have got a 0, 0. So that means it is not as simple as flat space-time. That means this metric tensor is not an identity matrix. It has got values. So if you go to my earlier videos, you will see that I have in special relativity, it is 1, 0, 0, 1, 0, 0, 0, 0, 1, 1, 0, 0. What does it mean? That means it has got no values. That is why in Minkowski space-time, where it is flat, measuring using that ruler is simple. But in curved space-time, it is very, 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 very difficult. No, I won't say difficult, but it is complex. Now, why it is complex? The reason is that in this kind of a scenario, you will find that things are taking values. So you have to compute the r squared, sine squared theta, and all those values will come. So that is why it becomes a little bit different. So that is the reason that things starts to take a different kind of a change. So what we can summarize is that metric tensor is a mathematical tool. That means a ruler. You pick up your daughter's ruler, you will find the same thing. It defines how distances and angles are measured in a curved space-time, and the metric actually changes because the distances might shrink, might bend, change, and so on. Okay. Now we come to the lambda part. Now, when Einstein actually, I would suggest you to read this book. I'm putting it up in the chat box. It is there over there. I can see this book on my shelf. It is called Brilliant Blunders by Mario Livio. Okay. Here you will find it is all about the brilliant problems which people have made, like Einstein. Can we apply maximum value of curvature before singularity? We can, but it will lead to infinity. That is the problem. I'll come to this part later. So Brilliant Blunders by Mario Livio actually talks about this cosmological constant in detail. It's about 7 famous blunders made by scientists like Linus Pauling, Charles Darwin, and Einstein is also there. So this is a very good book. So lambda actually tells that when Einstein introduced, there was no Hubble discovery. So Einstein thought that the universe is constant. Okay, so it is called a static universe. So what he thought is that if lambda is less than 0, then the space would pull inward. If lambda is greater than 0, then there will be a big bang or a stretching, etc. So that is what the thing is, that it either contracts or expands depending upon this. So Einstein called it as a brilliant blunder. because after the discovery of Edwin Hubble, we found that the universe is accelerating. But remember, this lambda is now actually considered to be a candidate theory for dark energy, dark matter. Okay, so originally this is the equation when there is no lambda in Einstein field equation. So the universe must either be expanding or contracting. So he put as a kind of a constant. So this was shocking because it contradicted. So if gravity pulls inwards and gravity pulls outwards, the terms acts like a repulsive force. Okay, it pushes space outwards, and by fine-tuning lambda, Einstein hoped to balance that gravity. So either it is pushing inwards or outwards. This was a balancing force. So now it has become very important because the entire operation of dark matter, dark energy is coming through this lambda, the cosmological constant. So cosmological constant is what? It is like a built-in energy. And Einstein first introduced to keep the universe static and later dropped it out. And now it is back to explain what is called dark energy. So now you can see we have done with R mu nu. Again, repeating, this is the Ricci curvature tensor. Next is the scalar, that is the average. Then we came to lambda, the cosmological constant, the G mu nu, which is the metric tensor. That is, it distances, measures the distance, etc. Now, so left hand side is done. Okay, completely we are done with left hand side. So the left hand side, what it tells how you measure the curvature. So you got the scalar, etc., etc., etc. Now, what is causing the curvature? So if this is the curvature, what is causing the curvature? Mass, matter. But matter is not as simple as the Newtonian matter. So this is now being done in a stress energy momentum tensor, T mu nu. That means everything you can see here. Pressure, energy, shear, stress, everything is taking inside a tensor. I will, if you want, you can put up a request. I will make a separate podcast, live session on tensor analysis. What is a tensor? Why do we need tensor? That will take another 1 hour time. So stress energy momentum tensor is actually responsible for mass. So what causes curvature? Mass. And what causes mass? Stress energy momentum tensor. So all this T mu nu 1 1, this is a symmetric tensor. Remember, just like metric tensor, this is also a symmetric tensor. Now you ask me what is a symmetric tensor? I won't answer right now. There's a lot of implications called parallel transport, etc. So stress energy momentum tensor. How does the matter causes the curvature? So I have already explained that. How does matter causes curvature? It's basically of the stress energy tensor. So stress energy momentum tensor accounts for the mass. So here I was just telling you. So now you know, see that left hand side is measuring the curvature, right hand side is measuring the mass. Okay. So here you can see that if I, what is dust? Okay, a very good question by Abhik Hazra. Oh, okay, I have to stop the screen sharing. So Abhik, dust is basically, it's a very good question. When we deal with stress energy momentum tensor or any kind of a matter movement, we assume a small, what I would say, it is a kind of a minimal perturbation in space-time. Let us define in that way. Okay. So a minimal curvature of space-time, or a very small thing, which is called a dust. Okay, now why we are taking a dust? Just the same way we take what is called a perfect liquid. Okay, we have many types of liquid, but we take a perfect liquid. So dust is basically a small speck. You can think of a small grain of salt or something like that, where there's a minimum perturbation. That means all my tensor components, the field equations, won't be getting too much in details. So there is minimal perturbation, minimal movement. So we call it as a dust. It is not a pure matter, because if you put a pure matter in Einstein field equation, Abhik, there will be a lot of problems. I hope I can make things clear. So dust is the minimal perturbation, a very small thing. And this will actually help you to understand how the field equation evolves. Okay, so that is why it is called a dust. Technically, what you can say is that it actually means a collection of very small solid particles. Okay, and in astrophysics or in cosmology, it is made of I would say carbons, okay, or ice grains, etc. So in Einstein's relativity, dust is basically it is used to describe a collection of particles. As I told you, matter, molecules, etc., which moves under very low gravity. Am I being able to make you clear, Abhik? Let me know. Very low gravity and have no pressure. So if this is a very low gravity, ideal exact solution. So rho sign is where the mass density of the dust. And if I take u mu, then it would be 4 velocity. So dust is not grains that you swipe from your dashboard. Okay, it is basically a perfect solution and idealization of matter freely falling in space. So it is used in cosmological models so that we don't get any further problems in order to, what I would say, too much of matter, too much of particles, etc. So it is, in cosmology, it is used that how intergalactic dust particles behave. It is an ideal situation. I hope I can make you understand, right? Okay. Is it all clear to you, Abhik? Let me know. Okay. So here you can see that this is the energy density is the diagonal part, rho. Okay, so that is why we call it as a symmetric tensor. So just as Abhik was telling a dust, then this is a kind of a perfect fluid. So if I put this in a perfect fluid, it looks like this. Okay, so we come to the freely falling space, falling inwards or what? Freely falling. It doesn't say whether it is inwards or outwards. It is just freely falling. So the stress energy tensor actually is like a kind of a master record. It tells how matter and energy are freely distributed. Okay, here we come to this. Okay, it is now clear to you. Thank you very much, Abhi. Thank you very much. So here you can see that mu nu is basically the dimensions of space. So 4 plus 4 plus 4 plus 4. So how many equations we are getting? 60. So each mu nu is 4-dimensional space and time. So is it equation or equations? Yes, these are equations. So now you can see how stress energy tensor is related to flux of energy and moment at a particular point. This is Bhima Raju Acharya. So yes, stress energy is definitely related to flux of energy. What question that you are asking is out of the scope of today's live video. Bhima Raju, you can get in touch with me. There is a mathematical derivation which shows that flux of energy and momentum is basically measuring at a particular point. So we need to calculate on that. Right? Okay, so here you can see 4, 4, 4, it makes up 16. So whatever you are seeing, it is a collection of 16 partial nonlinear differential equations. Now you might ask me that do we need to solve all those 16 partial equations? No. So that is why I have written there is a good news. And the good news is that some of the tensors are symmetric in nature. So 0, 1 equals to 1, 0. 0, 2 equals to 2, 0, 0, 3 equals to 3, 0, and so on. Okay, but remember that we are not cancelling things. I will come to this part. We are not cancelling things because we deal with, I will come to this part. So, same with Ricci curvature tensor, same with metric tensor, same with stress energy momentum tensor. So some of them are what we called is a symmetric tensor. Now you can see here. So if I plot 0, 0 and 1, 1, so if you go with this, the time equation, which is sourced, yes, R absolutely. R13 will be R31 and so on. So here you can see the XX equation and those, if you plot, then the value reduces. So even though Einstein field equations involve multiple tensors, the Einstein tensor is basically remaining of the 10 equations. Okay, so here remember one thing which is important is that the diagonal elements, so it is not cancelling out. Okay, it is just that we are not considering this because they are symmetric. We are not considering them, but they really don't cancel out. It is not a question that it is cancelling like AB cancels out with BA. No, we are not considering that. Why? Because they are of the symmetric nature. Here comes a very important point. Now, we know that this is where the limitations of general theory of relativity or Einstein field equations come. Now, if I take this bottle through which I was drinking water, you see that if I take this bottle up here and if I try to measure this dent, say for example, here is a curvature, okay, and I want to measure the curvature through Einstein field equations or whatever. Now, remember this curvature which is happening, this is something very local in nature. That means around this region only. So Einstein field equation, similarly, when we talk of cosmology, etc., you will see that this is something which is very local in nature. You will soon see that I am floating a series of videos starting from tomorrow on differential geometry, because differential geometry is very important to understand Einstein field equation. So differential geometry and topology, if you take two things, what is the difference between two things? Differential geometry is this one, which is very local in nature. The curvature is something local, but topology is global. So if I take Einstein field equation, the limitations is that it is local in nature. It cannot be taken globally. So what do we want if we take globally? It has got limitations. It has got problems. And that is why quantum field theory or quantum gravity or string theory comes in play. So remember, this was actually first observed by David Hilbert. To some, he is even more intelligent than Einstein. And David Hilbert thought that why don't I extend this local nature of Einstein field equation to a global nature? And that is why we have something, I've got many videos on my channel called Einstein-Hilbert action. In Einstein-Hilbert action, this is extended to a Lagrangian, which is much more global in nature. So let us look in this. It is local in nature. Now, here you can see, when we say Einstein field equations local, it means it is related to a specific point in curvature of space-time. So here you can see that if I am pointing my finger on a particular space, the dent you make is caused by a finger right there, nowhere else. Are you getting my point, all of you? Please do let me know. If I'm putting my finger, which is causing a dent, it is local in nature. It is not 10 meters away from this place. Similarly, if I put a box on a plane and it is causing a curvature, it is also local in nature. So G mu nu x means a parameter which is local. Okay, Abhijit is telling great. Okay. T mu nu x means something which is local. So the presence of mass and energy, whatever wrapping, etc., warping of space-time, is something which is local in nature. Okay. So here you can see that here I have written on the left-hand side, the Newtonian mechanics, that is something which is non-local. Okay, if you take in that way, that Newton's law of gravity is non-local. Why? Because it says object 1 instantly feels the gravity of object 2, no matter how far they are. So if I have two objects, which is here and here, Newton's law says that if they're infinitely apart, they're separated far distance, both of them will feel the same gravity. And that is what the inverse law of gravity tells us. So Newton's law is something where it is something which is not local, but general relativity tells that the interactions are local and is mediated by the curvature. So I have written this because I'm not going to explain this part in the video. This was further extended by David Hilbert, which is called Einstein-Hilbert action. And you can see that the integral sign, it is integrating all the volumes and it is taking the Lagrangian. And this limitation, why it came out, it is because of the tensors. It is because of the differential equations. And a differential equation means what? So if I want to measure the curvature of this bottle, I will use the differentials, right? But differential means it is local. So I was making this video, sir, in Einstein-Hilbert action for calculating, does it require mass? Yes, it requires mass, but it is a Lagrangian density of the mass, not the general density. It will take a Lagrangian density. I have made a video, you can watch it later, this channel only. It is very detailed, called Lagrangian density, why it does. So what I'm trying to make a point is that if you want to extend that, we cannot do, because differential equation is local in nature. That is why differential geometry is one of the key components of general relativity. But topology is different. Okay. So that is why here you can see I have told that this is something which is very local in nature. And from Einstein-Hilbert action, I can come back to Einstein field equation. So if I take you see S equals to integral of C4, etc., etc. So this is an integral over whole space-time, not something local. So it is non-local in form. So local theory is one where what happens at a point in space-time depends only on the space-time itself. So the action principle, which is the principle of least action, the action itself can be global, but the field equations are derived locally. That means differential equation. That is the difference. So Einstein-Hilbert action, or whatever we are doing, this is taking the action principle. That means the particle is globally and naturally evolving in time. But here the particle is evolving due to the curvature of space-time. And this curvature is local in nature. We get all the things which are very local. So this part of the video and our discussion actually ends over here. We now move, sir, I have pinned messages in WhatsApp. Okay, great. Now we will come to the next part, is that all are done. But as we say that there are certain limitations in terms of Einstein field equation. It is not always good equations, but behaves local. Absolutely, you're right. So in this part of our discussion today, we will come to understand what are the limitations. This is important because otherwise you will never understand what are the new researches which are developing. Like, for example, Indra Roop and others who would be going in cosmology and general relativity. So you need to understand, because you will be working on extending Einstein equation. Whatever Einstein has done, it has been done. Okay, we cannot make changes to the field equation, but we can definitely extend it. Okay. So the first proof of general relativity, this is a very interesting history. I don't know whether you are aware, is called the perihelion precession of Mercury. Now, perihelion, so what perihelion means what? Precision. So there are two words, precision and precision. So precision actually means that when things revolves around an axis, how it actually changes, it wobbles. Okay. So as I have written on this text is that in mathematics, you can make a proof through axioms. But in physics, it is not like that. Physics, the proofs actually changes. So what is the proof today in this air-conditioned room? It will change if I switch off the aircon and things will change. So the precision actually means that it refers to the slow gradual movement of an orbiting body. So in English, don't get confused. I also teach English, by the way. Precision and precision, same pronunciation, but two different meanings. Okay. So here you can see that it was observed that Mercury is going around the sun, okay, which is called the perihelion, but that has got a change. And this slow rotation is called the perihelion precession. So observed precision was 575 arc seconds per century. Explained by Newton was 532. So 575 minus 532 would be 43 arc seconds. That is a real problem in the brain. So there was a mismatch. And this mismatch, nobody was able to understand until the genius of Einstein actually came in. So that 43 arc second was a pain, a big pain. So this is again, I think you're enjoying these illustrations. Do let me know, because I made a very big prompt in ChatGPT to make this equation, this photograph, and I really enjoyed that. I put it up in my WhatsApp status also. So the mass is causing the curvature of space-time. And what is happening is that because Mercury is closest to Earth, Sun. Okay, thank you, Abhijit. So because Mercury is closest to Earth, Sun. So because the Sun has got a heavier mass, so the dent or the curvature is more. So Mercury could feel that curvature. And Newton's equation was unable to predict that 43 arc seconds. So Sun's mass curves space-time. Mercury is near, so it feels the curvature. And the curvature causes its elliptical orbit to rotate, and slowly the perihelion advances. So that is actually the reason. So the precise calculation of general relativity actually predicted that 43 arc seconds. And this was actually done with his friend, Michel Besso, who was I think an Italian mathematician. And he was a very close friend of Albert Einstein. Together they calculated. This is the first page which is showing Einstein's handwriting. And this was the first test which actually explains that yes, general theory of relativity is correct. I downloaded this somehow. This is called the original handwriting of Albert Einstein. I got fascinated. So this is written in German, which tells precision in 100 years. Now, you might be thinking, why 100 years? Because that arc second is so minimal So minimal that 1, 2 or 3, 4 or 50 years won't make any change. So you have to actually calculate 100 years to actually get something formidable, some kind of a quality. So this double apostrophe means arc seconds, and it shows that independently verified. That means other researchers also calculated and found that this is correct. This is independently verified. So this is a handwriting of Albert Einstein showing the different things. And I'm not going into this. This is how he actually calculated, and this is the flow. So it shows that space-time curvature predicted by general relativity is real. So as you understand that even Einstein faced the criticism, nobody actually believed that he was writing things right. So perihelion precession of the mercury first showed that yes, Einstein is an intelligent person. He knows some amount of mathematics and he is correct. So that was basically predicted. This is also from AI. So this is actually called the Eddington experiment. So Arthur Eddington, English mathematician, he went to on the 29th of May, very special day for all of us, calculated preciously. Yeah. So you can see here that they were measuring, and this was again a solar eclipse. So during that solar eclipse, there was a deflection, and this was actually 0.87. Einstein said 1.75, and Eddington's data perfectly matched with Einstein. So the first direct evidence that mass curves space-time. So this I have already shown. Other various proofs came up: gravitational redshift, then gravitational lensing, gravitational time dilation, and recently, I think it was what, 2010, Abhijit, if I remember, when the gravitational waves were being detected. So these are also proofs of general relativity. Okay, what are the consequences? This is very important to discuss. So now let me, here we will try to understand. Now, when we talk about the consequences, we need to understand that what really happens when we try to solve Einstein's field equation. This is where the cosmology and other parts come in play. Now, so what happens when we try to solve this equation, x plus y equals to 2? So you're given a value x, you're given a value y, you put it up and it results to something. So Einstein field equation is also the same, isn't it? You have got something in the left hand side, something on the right hand side, you pull in some data, x, y, z, and you get a value. So that is actually what happens when you solve an equation. Now here you can see that if I take a simple equation, f equals to ma, and if I take, say for example, f is 0, there is no force. So what will happen? X equals to vt plus x0. That means the body moves in a straight line with constant speed, say for example. Now, typically in Einstein field equation, if I take who was asking that dust question? I think Abhig Hazra. What is dust? So here you see Abhig, the concept of dust comes in. So if I take the matter and energy as 0, that is what is called a dust. I am assuming there is no matter in the universe, for example. And if I take T mu nu, that is the matter content, to be 0, then what we get is a flat space-time. Flat space-time means the values would be 0, 1, 1, 0, 0, 0, 1, 1, something like this. It is a flat Minkowski space-time. And the metric will be something like this: ds squared is equal to minus c squared dt squared. Now, if you're really wondering what this minus sign means, I've made a complete video on the courses section of General Relativity. You can find it out. So this is how the metric looks. So there is no mass, things are simple. Now, say for example, we take a sphere, the dust concept, very low gravity, very less amount of energy. And what we are trying to do is that if we try to solve Einstein's field equations using this space-time metric, then what we get is what is called a Schwarzschild metric. Here you can see what is the Schwarzschild metric. Don't worry about this big equation. What it tells is that, is this video considered to give general information? I don't understand. What do you mean by general information? We are learning general relativity, so we are taking this into account. I don't understand, if you can clarify. So this is what is called a Schwarzschild radius. So even this bottle can become a black hole. If I can find out the Schwarzschild radius of this bottle and I squeeze it below that, it will become a black hole. So now Schwarzschild is a brilliant mathematician. Remember, he actually calculated Einstein, first person to calculate Einstein field equation. And I don't know whether you know this fact. He was serving in First World War, and he was lying inside the bunker without any computer and smartphone, with a pen and a paper. He first calculated the Einstein field equations. Brilliant. I mean, so that is how actually people work. Under the bunker during First World War, he calculated Einstein's field equation. Solutions. Solutions means what? That if I put the values inside, right, and what we get is basically a short. That means if I go below this radius, so you can see I have written, if I compress the mass smaller than Rs, which is the Schwarzschild radius, we get a black hole. Okay, so this is how what he can. So when he put in value inside Einstein field equation, Carl Schwarzschild found that, oh my goodness, this is happening something weird. So here you can see this is the metric which I have taken. So don't consider the right hand side, r squared, d theta squared, etc. I put it as d omega squared. So the left hand side of the equation actually tells how time ticks. As you move near and near the black hole, time slows down. And the second part is radial distances, how actually things shrink or stretches out, okay, when you approach a black hole. I will come to this part. And the right hand side is just the Schwarzschild overtook Einstein. In some sense, you can tell, yes, Schwarzschild overtook Einstein in some way, because anyway, yeah. So now here is a very important concept which most of the students I have seen in classes, etc., they always make a kind of a mistake. What is undefined and what is infinity? What is the difference? What is infinity and what is undefined? So most of us have a wrong notion telling that matter blows to infinity near black hole. Time goes to infinity. Is it really that it goes to infinity or it becomes undefined? So there is a confusion. Most of the people you see, they tell that either infinity or undefined. Now, first of all, let us see this part of our part. Yes, infinity is divergent series. So as Schwarzschild radius, the inside becomes 0. So 1 upon 0. If the radius is shrinking, and it is becoming 0, then the denominator becomes 0, and 1 upon 0 is undefined. 1 upon 0 is undefined, not infinity. But still the question is that why do physicists tell that it is undefined? So here is the answer. The answer is that if I take a value where r is equal to rs, then 1 minus 1 will be 0. So for r which is greater than rs, it will be a denominator which is a 0. Okay, now here you see what happens. What Abhijit was telling. Since the denominator becomes a very tiny positive number, like 0.000001. So if I take, for example, 0.0001, value will be 1000. If I take 0.00001, it will be 1000. And as I reduce the denominator lower and lower and lower and lower, okay, that means the upper portion will become bigger and bigger and bigger and bigger. So infinity is a divergent series. Are you getting my point? So that means near the black hole, as the value reduces 0.00, 0.000, further, the numerator or the entire equation blows up. That means the value will become bigger and bigger and bigger and bigger. That is why we call it infinity. So here you can see, instead of saying that undefined, physicists describe as a behavior going towards infinity. So that is why we say that the metric or the Schwarzschild metric diverges or blows up. So pure mathematics tells that r equals to rs becomes undefined, but physicists tell that we took the limit and it becomes infinity. Is it all clear to all of you? In the infinity and the undefined part, this is important. Technically, you should be correct. So technically 1 upon 0 becomes undefined, but because this value here becomes smaller and smaller and smaller, we put lower smaller values, 1 upon this, 1 upon further, 1 upon further, it becomes infinity. So that is why in all these films, etc., like Kip Thorne's Interstellar, etc., you will see that it grows up to infinity. Technically, it is undefined when we do the mathematics, but here it actually goes up to infinity. This is again my diagram. So black holes are not assumed, they are actually a part of the equation. So from an outside observer, the time stops, or you cannot see it, and it stretches and stretches. So naturally, Einstein here is smiling, because 1 upon 0 to undefined now becomes up to infinity. So black holes are actually natural mathematical consequences. I am just skipping this part because you already know clocks run slower, extreme gravity traps everything inside, light flows, massive objects in motion create ripples. So these are actually a kind of what I would say, consequences of general relativity. Now, so what are the limitations? So limitations are this. Singularities happen, and we mathematicians and physicists, we don't like singularities. When we try to join this with quantum mechanics, what happens is, it is a classical theory, so the universe does not run on quantum scales. When we try to join this, it becomes renormalizable. That means infinities happen, and general relativity beautifully explains how visible matter, but they cannot explain the galaxy rotations and dark energy. So here are the limitations. It breaks at singularities. It predicts infinities. We have just seen infinity, isn't it? Schwarzschild metric. It is not quantum in nature. That means it is actually not helping you out in terms of infinities. It is not renormalizable. That means infinities will continue. And because it is local in nature, it is limited testing range. So that is why we say general relativity is powerful but incomplete. Now, how will we make it complete? This is where the alternative theories come in play. And I'm just going to take up this theory, which is a little bit pretty old, but simple to answer. So the first important theory was taken up by Robert Dicke and Carl H. Brans. So if time runs slow, there is a curved space. If curved space, then subatomic particle works of that time. Yeah, right. So Abhijit and others, those of you are very young, you need to understand this part of the today's video, today's live, because here is where you need to work out. Here is where the equations actually come in play. That means we are going to extend Einstein's field equation so that we avoid the problems. What are the problems? These are the problems: infinities, singularities, etc. So the first serious, there has been a lot of attempts, but the first serious theory came from Brans Dicke theory, or Brans Dicke Jordan theory. Don't worry about this huge equation. It is nothing but what they did is that they don't assume gravity to be constant. The big G, which is the Newtonian constant, they replaced that with a scalar field phi. Okay, so scalar field, why? Because gravity strength becomes dynamic. So here you can see here. So in a scalar field, they are following the same Newtonian law. G is inversely proportional to 1 upon phi. So what they thought is something like this, which I am showing with the bottle analogy, that its gravity is changing from this part to this part to this part to this part. Why they are thinking? Because this is bending. I'm not going to crush that. It is going to spill over. So if this is bending something like this, so for example, if I take this kind of a part, and if it is bending like this, okay, so what is happening? Gravity, which is very local in nature, is going to change because the space-time is bending. So what they thought is that if gravity is bending, or the force of gravity is changing with the space-time curvature, then there has to be a function or a value which keeps on changing. Okay, so they introduced this concept phi. Why it is scalar? Because scalar will make things easy, isn't it? Vector will have a magnitude, direction, etc. We make it a scalar field. And the same concept is followed in Einstein-Hilbert action. So I always tell my students that before going to Einstein field equation, please understand Einstein-Hilbert action. Most of us don't pay any attention to Einstein-Hilbert action because it is not popular in nature. Okay, so here you can see that in case of f equals to g, if I put f equals to g of t or g of x, so we are putting in a parameter. So the idea is that gravity is not purely geometry. There is a new scalar field phi, and this modulates and change. And a Brans Dicke theory tells that g is not constant. So that is why they use the scalar field, because it is naturally suited for coupling to scalar quantity. Introducing scalar field phi is simpler. Vector has got lot of problems, strength of gravity, etc. So scalar field acts like a cosmic bookkeeper. That means it adjusts to the local dynamics of the gravity which is happening. Okay, so here you can see this entire huge equation. What it tells is that gravity is not only shaped by space and time like Einstein, but it is a scalar field that decides how gravity is at different times in different places. So instead of a fixed gravitational constant g, the universe itself can change. So Einstein general relativity tells gravity equals to geometry of space-time, but Brans Dicke theory tells gravity plus v phi, which keeps on changing. It's a huge complex thing. If you read the original paper, full of difficult complex equation, but overall this is one of the alternative theory. So what is this picture all about? I have imagined Einstein is in a concert hall and he is playing this one. Okay, he's playing the concert, and here what happens is that the concert actually plays one single sound or one single drum. Okay, I will just put up this link over here. You can watch this video later, and this is actually a detailed video on what we discuss, so you can pause and watch it later. It's almost a 1 hour video. You can take a note of that. I put it in the comment box. And Brans Dicke theory is telling that no, it is not a single music or a drum. It has got many things which are changing. So that many things which are changing is basically the phi, which is called the scalar field. So you can pause this, and you can understand what it is actually. So Brans Dicke theory, FR gravity, different types of Mond, loop quantum gravity, string theory, the different kind of alternative theory, what it changes, purpose, and I'm not going in that because it will again take a lot of time. It is already 1 hour 22 minutes. So this actually tells what are the alternative theories. And finally, we come to the last part of today's live session, in search of quantum gravity. So what it tells is that general relativity works very well with large things. Quantum mechanics works with very small things, and we are looking for some kind of a marriage. Okay, general relativity with quantum mechanics, that is basically the entire research all throughout the globe which is going on to find a quantum gravity. So what is that? That if general relativity is something on a very smooth manifold, which is a space-time, quantum physics is discrete, Planck's constant, etc. So energy is discrete. So what we are trying to do is that we are trying to quantize gravity. That means gravity, which is considered to be something which is very smooth, will be quantized in numbers. Okay. So it is just like, say, for example, we are telling light, which is coming in a classical Maxwell form. Light in a classical Maxwell form. We are trying to quantize that in a form of a quantization. So we need to unify our framework of quantum gravity. So there are different approaches of quantum gravity. These are not yet been established. So we cannot tell what actually it is. String theory, which thinks particles as vibration in string. And Professor Leonard Susskind, all of us, we know, is the great guru of physics and mathematics. He is actually the father of string theory. So graviton is a kind of a mediator. We have gluons and we have photons. So we are still searching for what is called a graviton. Then we have got a loop quantum gravity. You have heard the name of Professor Abhay Ashtekar and Ashtekar variables. These are actually, certain things which are called loop quantum. So loop, it actually takes loops which are woven in a kind of a spin, which is still under the way. So these are researches. There is something which is called an asymptotic safety, where you take a fixed point and where the infinities try to cancel out, but it has not been yet established. Then there is called a CDT, or the causal dynamical triangulations. So I'm not going to explain this because these are all under the way, which is basically to marry general relativity with quantum physics. And if you talk, there are different approaches. Is in string theory which type of math? This is a very good question, Raghav. Lot of different mathematics. The Lagrangian is used, very complex. very difficult to explain right now. I have to show you a lot of mathematics is used. Perturbation theory, non-perturbation theory, huge amount of mathematics are used. So very difficult to explain that. So one is the particle physics approach for quantum gravity. So what is the idea is to treat gravity like other forces, and the method is quantize gravitons. So that is one method that is called the perturbative or particle physics approach. Next year, you can see what is called a non-perturbative. That means what it tells that space-time do not emerge. It has existed before. So that is what it is called loop quantum gravity, CDT, all those things. This is non-perturbative. That means there is background in it. There is no background. It is emerging out of that. So these are very difficult to explain non-mathematically. And then we have got an emergent gravity approach. So Verlander theorem is holographic, same the holographic principle, the ADF, anti-de Sitter and CFT correspondent, etc. First one converted Einstein GTR into quantum phenomena. Yeah, absolutely. So that is all. That is the last slide of today's lengthy. General relativity is not the final word. It is a chapter in our ongoing quest. Quantum mechanics and relativity are still not united, and we are waiting to find out a theory which will harmonize. The universe keeps secrets yet to be being unveiled, and perhaps the deepest lesson is waiting for us. And the truth is what becomes stranger than fiction, and the truth is always bigger than our current equations. So that is all. You can follow me in my Facebook page, which is the Physics Compass. You can follow me also on my thread on LinkedIn, and in Instagram. I am not posting at all physics because I play piano. So I put up a lot of Beethoven's music, a lot of wildlife, and a lot of other things, science fiction, etc. So you can follow me in Instagram also. I'm there in the name of Physics for Students. So that's all. I hope you enjoyed today's session. And if you have any questions, please do let me know. I will be happy to answer for another 10 minutes. How was this session? Did you all enjoy this? Let me know. If you have any criticisms also, you can put me up. If you want to support me, you can pay a little bit of thank you button, put up a thanks, what you call, thank you, and a kind of a small token amount to me. It's up to you. Yeah, Jim Romansky, he has always been a supporter of my channel. He paid me a lot of thank you, sir, and what you call, I forgot that, super thanks. Jim Romansky has been a person who always gave me in dollar super thanks. Thank you, Jim. He has been a tremendous support. Math should be humans' first language. I wholeheartedly agree to that math should be a kind of a first support. And I think that Jim has actually, so that is why supporting to what Jim has told, I always tell the students, oh, thank you, Jim, for giving $5. Thank you very much. I was just so thank you very much, Jim, for your support. I always tell my students that a person who can do mathematics can do everything. You can do literature, you can do geography, you can do everything. So please concentrate more on mathematics. Keep on supporting to my channel. Okay, Abhijit Kumar, thank you, amazing. Thank you very much. Abhijit, you have been a tremendous support. Vincent Pinto, I think you are from Brazil. So thank you logging in from Brazil. Thanks for your presentation and effort. Excellent. Thank you very much. And thank you, Jim. It has been a small amounts, always counts. It has been a tremendous support from you all. So that's all for today's lecture. And, I will try to, come online frequently because my daughter's examination is around, as you understand. She will be giving her ICAC next year. So I don't get enough time because we have to sit with her. My wife is a master in philosophy. She has been doing a lot of researches in, Vincent Pinto, you're from Bangalore. Great. So she is doing her researches in Goodell and philosophy. So she is busy with my daughter. I keep on supporting. So I really don't get time in the evening after coming, making videos, etc. So I will try to come online again after the 20th of September because my daughter's this semester exams will be done. Do let me know that what kind of podcast you want. I think I should make one on quantum field theory this time. this would be too interesting also. So thank you very much. Special thanks to Jim, Abhijit, Vincent Pinto, Abhijit Kumar. Who else are there? I'll take the Walter. Walter is there. Somnath Safi, Indrarup Sen. Thank you very much, all of you. Rudra Pratap Singh, Raghav Manchanda, all of you have been supporting me. I've been making videos. So I will tell you, just to announce quickly, on the 6th of September, starting 7 p.m. Indian time, not 8 p.m., we have a very important podcast on general relativity. A very important lady, a nice speaker would be coming. I will announce it in due course of time. And there will be a spree of videos coming up from tomorrow. Those who wants to understand differential geometry, what books you read, what are the things that you will do, I'm making on that. Those things should be there. So yeah, that's it. Thank you very much. Do take care. Please keep yourself healthy, happy, spread the light of wisdom, knowledge, and learn mathematics. As Jim has rightly told, that mathematics should be the first human language. I wholeheartedly support with Jim. With that, let me give you a big thank you for joining me today, and see you soon. I will be there in WhatsApp. I am there in Facebook. I am there in my thread. I am there on my email. So any question, please do let me know. Thank you very much, and may the good Lord be with you. Thanks. I will try to tune you more. Thank you, Walter. I know you are from US, so it is the time won't match. Do watch my channel, Physics for Students. If you want to take a subscription, Walter, you're all welcome. A lot of videos are there, and a lot of videos are coming. Some of the videos are old, so I would apologize. Those are not in a good shape 3 years back, but I'm trying to improve my quality day by day. Thank you very much. May the good Lord be with you. Thank you, Jim, and thank you everybody for joining. Goodbye.